So, Margaret, can you see my slides in the back?
Yes, I can see you. Oh, they vanished.
Let me see. Is it now?
Yes.
No, we can't
Wonderful.
see them.
Thank you. It's because. Okay, great. So, let's start. Good afternoon, good morning, or good evening, depending on where you are joining us from around the world. On behalf of the Radiation Protection and Nuclear Safety Youth Network and the Women in Nuclear Innovation Group of WIN Global, it is our great pleasure to welcome you to the third session of our Holistic Radiation Protection Perspectives webinar series titled as Radiation Routes from Oil Wheels to Algorithms. So for today's program, we have a very great agenda, and this series was created to inspire, connect, and empower professionals and students who are passionate about radiation protection and nuclear safety. It is a safe space where we bring together technical expertise, integrational dialogue, and global collaboration, all with the goal of building a safer, more inclusive, and more innovative nuclear future. Today's session is particularly exciting, and we will explore the fullest spectrum of radiation protection, from the challenges of managing natural occurring radioactive materials in the oil and gas industry to the cutting-edge tools used in radiation transport modeling. Our speakers come from diverse backgrounds and regions, and they each bring a unique perspective to the conversation. Before we begin, we would like to express our greatest gratitude for all of you for being here, whether you are a student, researcher, a policymaker, or a practitioner. Your presence and participation are making this community so vibrant and meaningful. So this is the agenda for today. And before we start the welcoming speech, please allow me to introduce each great guest that we have today in the house. So I would like to start first with Mrs. Eva Gianni. She is a WIN Global Technical Leader and WIN for Peace Leader at WIN Global. Mrs. Eva is a senior nuclear professional with more than 40 years of experience in the field at the international and national levels, having worked at the IEA as a nuclear safeguards inspector and in other positions in the Department of Safeguards, as well as the United Arab Emirates Federal Authority for Nuclear Regulation as a senior export control specialist at the IEA. She was the Senior Inspector for Implementation Coordination in the Iran Task Force, overseeing the work of inspection teams during the preparations for the implementation of the Joint Comprehensive Plan of Action, well known as JCPOA. Mrs. Eva is actively involved in Women in Nuclear Global, where she holds the position of technical leader and leads the group WIN for Peace, and she was the president of WIN IEA from 2009 to 2016. Please, Mrs. Eva, the floor is yours. Thank you.
Thank you very much, Florencia. So for me, it's good afternoon from Vienna to all of you who have joined, and thank you very much for participating in this third series of the webinar entitled Holistic Radiation Protection Perspectives. So today's webinar is entitled Radiation Sources from Oil Wells to Algorithms. So you may be wondering what this title really means. In general, our technical experts who are invited to this series of webinars discuss advancements, applications, and future trends in this field. And today I would like to, before we start, first of all, give a special acknowledgement to our host, Ms. Florencia Renteria, whose commitment to nuclear advocacy has been a source of inspiration to so many of us. Her energy and enthusiasm for nuclear are just breathtaking. Yesterday, she finished the last day of the Nuclear for Newcomers Summer School. Then she worked half the night to issue the certificates to the speakers and the moderators, and she's now back here at 5 a.m. Mexican time to host this webinar. So a big thank you to you, Florencia, and congratulations on putting this all together. So Today's session will focus on the latest innovations in radiation detection and measurement technologies, in particular related to the field of transportation of such materials. We are fortunate to hear from 3 experts who will bring together regional perspectives and technical depth. The first one is Mr. Mohammed Salah, a radiation physics specialist from Egypt, who will guide us through radiation protection from NORM. You know, NORM is naturally occurring radioactive materials in the oil and gas industry, in particular during NORM transport. Our second speaker will be Dr. Valeria Starovoitova, who is a former Radiation Technology Coordination Officer at the IAEA. She will introduce the latest digital tools and modeling approaches to be applied for radiation protection during transport. And last not least, our third speaker will be Dr. Victoria Herzner from Austria, who is representing the IRPA Young Generation Network. She will speak about IRPA, what is IRPA, and the Young Generation Network. At this point, I would like also to mention that in 3 weeks' time or 4 weeks' time, there will be the IRPA conference 2025 in Abu Dhabi. I think it's from the 7th to the 9th of October. I hope many of you who are here today will be able to attend, or at least some of you. I will be there as well, so I hope to meet you in Abu Dhabi in 4 weeks' time. We will also have 2 moderators from Kenya, Miss Margaret Chege and Mr. Edwin Kagai, who represent the next generation of nuclear professionals. They work in their home country, and their work highlights how youth engagement and academic leadership can strengthen radiation protection in their region. Florencia has also mentioned my work over the past 40 years, and those 40 years have taught me a few lasting lessons. First of all, technical excellence matters, and robust science and careful practice are the foundations of safety. Secondly, international cooperation is essential because radiation protection transcends borders. When we share knowledge and build common standards, this benefits not only us, it benefits everyone. And third of all, inclusive leadership makes a difference. Bringing diverse voices into the conversation leads to better decisions and stronger trust. So, in my opinion, radiation protection is not just a technical exercise, it's also a human one, because our work protects lives, preserves environments, and helps build trust between communities and institutions. When we place people and ethics at the center of technical work, we ensure that nuclear technologies serve the common good. And this is exactly what we need nowadays in order to make the general public accept nuclear energy as a safe and clean energy source without any mistrust and with full confidence. So, before we begin today's session, I invite you to engage fully, listen carefully to the speaker's experiences and insights, and then don't be shy to ask any questions you may have. Don't be shy to ask. Don't think your questions are stupid. Just ask them. There is no such thing as a stupid question. And you will have the opportunity to ask any question at the end of each presentation. So, thank you again to the organizers, the speakers, the moderators, and to all of you for being here. And I look forward to our learning experience from this session. With these words, let me hand back to Florencia. Thank you very much.
Thank you very much, Mrs. Eva, for that inspiring message. And it really touches our hearts. Thank you so much for being a mentor, a role model in the industry, and keep supporting us all the time. So we are very valuable for everything, I would say. So now it will be my great honor to introduce Edwin Kagai is a dedicated radiation and environmental physics final year student at the Kenyatta University and the Secretary General of the Radiation Protection and Nuclear Safety Youth Network, RPNS-YN. He is also the Kenyan representative to the International Radiation Protection Association Young Generation Network, IRPA-YGN, and he's passionate about radiation protection, nuclear safety advocacy, and empowering young people to actively shape the future of nuclear science and technology. Edwin is passionate about combining his studies with community initiatives to inspire youth involvement in science and safety. Please, Edwin, over to you. The floor is yours.
Thank you very much, Florencia, for this chance. I am Edwin Kagai, as I have been introduced. Mine is just to briefly introduce you to know what radiation protection and nuclear safety is. We are a youth network in Kenya, and we were we formed this network in 2023 as at Kenyatta University. This one is in Kenya, and it was established by passionate students and young professionals. RPNS-YN is committed to promoting radiation safety and protection and awareness among the public, professionals, and stakeholders. The network provides a platform for young people to learn, to collaborate, and to contribute to the advancement of radiation protection practice, both nationally and internationally. So RPNS has personal, professional, and societal objectives. And one of the personal objectives is to ensure personal safety through understanding radiation protection principles, to enhance knowledge of radiation sources, the effects, and mitigation measures, to develop critical thinking, leadership, and problem-solving skills. The professional objectives include encouraging careers in radiation protection, such as radiation safety officers or health physicists, to promote continuous learning through workshops, conferences, and advanced qualifications, to support research and innovation in radiation safety technologies. Some of our societal objectives include raising public awareness about radiation risks and advocate for effective safety measures, to promote environmental protection through responsible use of radiation sources, to influence the development and enforcement of national and international radiation safety policies. RPNS have been able to achieve some achievements, and we also have some future goals. Some of our achievements is that we have achieved global collaboration. We have successfully partnered with ILPA, Young Generation Network, to organize this holistic radiation protection perspectives webinar series promoting international knowledge exchange. This holistic protection perspective, we have also collaborated very much with Winnie, and most of the Winnie experts are with us today. We have also been able to ensure advocacy and engagement. We have organized webinars and discussions to engage young professionals in promoting nuclear energy and radiation safety. We have established university chapters, and one of the chapters is fully in operational in Kenyatta University. We have also been able to register our network with the Kenyan government, and we registered our network as a community-based organization. This strengthens our legal recognition and capacity. So our future goals includes gaining international recognition through innovative campaigns and projects that will raise awareness on radiation protection. We also aim to contribute actively to the national dialogue and policy making to strengthen Kenya's nuclear safety and protection framework. So thank you very much. I am looking forward to interacting more with you. Thank you. Back to you, Lorenzo.
Thank you very much, Edwin, for those wonderful remarks and recognizing the great work all of you are doing in Kenya. Thank you for keeping those efforts high. So now I'd like to introduce Mrs. Victoria. Victoria is a radiation protection expert at the Austrian Agency for Health and Food Safety, focusing on clearance, environmental monitoring, and contaminated areas in radiation protection. She is also a PhD student at the University of Natural Resources and Life Science in Vienna, Austria, where she explores the radiation aspects of fuel combustion residues from a radiation protection perspective, focusing on cesium 137 and strontium 90 post Chernobyl. Victoria is a member of the Austrian Association for Radiation Protection and the chair of young scientists and professionals. Additionally, she is a member of the leadership committee of the International Radiation Protection Association Youth Generation Network, RPNS-YN. So please, Victoria, it's a great pleasure to welcome you, and we really appreciate the time that you're making for us to stay with us. Thank you. Over to you, Victoria.
Thanks a lot, Florencia. It's always really nice to be here and see what you are doing and listening to these well-organized webinars and talks. As member of the IRPA Young Generation Network, as Edwin also mentioned, he's also a member. It's really nice to have members in the IRPA Young Generation Network from Africa as well, because we try to get as many nations in the Young Generation Network to have the global, the international voice from the young generation. We try to help to set up new young generation networks in the different countries and support the young generation there. And for me, it's something I really enjoy to see what is growing and what is the build and where it is going. So if you want to also be part of the IRPA Young Generation Network, please reach out to Edwin or to myself. And if your country doesn't have a young generation network yet, please also ask us how we can support you or your colleagues and your country, of course. And I'm looking forward to the webinar, and I'm keen to ask questions afterwards. So thanks a lot for inviting us again.
Thank you, Victoria, for connecting across the borders with all the people around, and for your high spirit and commitment to the radiation protection field and beyond. So now I would like to hand over to my great colleague, Margaret Chege. Please, Margaret, the floor is yours to continue with the program.
Thank you very much, Florencia. And thank you for your warm welcome and for setting the pace for today's webinar. I must say that your dedication in co-organizing the webinar series on holistic radiation protection perspectives alongside a radiation protection and nuclear safety youth network team, and the role played by WIN Global and World Nuclear Association in bringing together people from diverse backgrounds. It is truly appreciated. I would also like to applaud the insightful opening remarks by Mrs. Eva from Women in Nuclear Global, Ms. Victoria for representing the International Radiation Protection Association, Young Generation Network, and Mr. Kagai, who, like Florencia has said, she's, and Victoria, she's not only the Secretary, RPNS Youth Network, but also the Kenyan representative to IRPA-YGN. She's also an undergraduate student at Kenyatta University. So my name, I'm Dr. Margaret Chege. I am a lecturer and researcher in the Department of Physics, Kenyatta University, Kenya. I'm also the patron and the advisor of the Radiation Protection and Nuclear Safety Youth Network. I am delighted to be this webinar moderator. As it has been said, the theme of today's webinar is radiation routes from oil wells to algorithms. And we are fortunate to have two experts in the area who are willing to share with us their insights and perspectives. And first, we will hear from Mohammed Salah, who is a radiation physics specialist and NOMAD advisor. Mr. Salah serves as HSC manager and radiation safety officer at NOM Solutions, Cairo in Egypt. He has extensive experience in naturally occurring radioactive materials, or NOM, and technically enhanced naturally occurring radioactive materials, which are commonly referred to as TENOM, management, contamination, and radiation waste handling in the oil and gas sector. Mr. Salah has served in leadership roles, including HSC manager, radiation safety officer, and non-technical specialist overseeing decontamination operations, safe transport, and storage of radioactive materials. Mr. Salah also designs storage repositories, conducts risk assessments, and implements radiation protection protocols for complex offshore and onshore projects. In addition, he is an experienced instructor and consultant in radiation protection, norm regulations, and safety standards, providing training and advisory services for industry professionals. He holds a bachelor's degree in chemistry and physics, a postgraduate certificate in radiation physics, and multiple certificates in radiation safety, occupational health, and HSC management. His talk today will focus on norm protection in the oil and gas industry. After Mr. Salah will shift gears with Valeria Starovoitova, an independent consultant on applied nuclear physics projects and a former IAEA officer. Dr. Valeria has over 20 years of experience in applied nuclear physics. For over a decade, she worked at academia, Purdue University and Idaho State University, USA, where she was involved in several projects such as feasibility of photonuclear production of isotopes, nuclear waste transmutation, and photon activation analysis. In 2013, she joined Neowave Inc., a private company that delivers and commissions superconducting electron accelerators. Her task was to establish and lead the applied physics group, which by 2018 grew to 10 researchers, including nuclear physicists and engineers, radiochemists, health physicists, and material scientists. From 2018 till 2025, Ms. Valeria worked at the IEA as an expert in radiation technologies. Currently, she's an independent consultant on applied nuclear physics projects. Her talk today will focus on algorithms to applications, tools for radiation transport, and modeling. And please join me in welcoming our first speaker, Mr. Mohammed Salah. And feel free to jot down any questions you may have on chat or question and answer section. And I believe our two speakers will be available to address them. Over to you, Mr. Mohammed. Kindly load your slides.
Thank you, Mr. Margaret, for your introduction. And let's kick off to that presentation. Can we?
Yes, please.
Okay.
We cannot see your slides yet.
Yeah, now, how about now?
We can see them now. Please proceed.
Yeah, that's great. Hello, everyone. I am Muhammad Salah. I am radiation physics specialist from Egypt, and that's it. So I will have around 1 hour giving you some or sharing some information related to norm in general and in specific in oil and gas. So let's start, please. Today we will discuss some process at oil and gas related to norm. We will know what is norm, where we can or might find that norm in oil and gas or in other application. We will focus on oil and gas. While doing this, we have some, let's say, some equipment or sub-equipment to norm or accumulated by norm that needs to decontaminate it. So while we're dealing with that norm, we need shore protection. And we need also, while doing this activities with norm, after collecting or decontamination, we need to manage or handle waste. After that process, we will go through storage or disposal. While doing this, we transferring the waste from storage or the disposal or final disposal facility. We need some regulation related to also radiation protection, which is transportation. That's governed by a nuclear regulator body in your country. So that's, let's say, this is a kind of summary for what we will go through in that webinar, inshallah.
Mr. Mohammed, if I may interrupt you for a minute, you have about 20 minutes to make your presentation, please.
Okay, I will make it fast. Okay. So let's start with what we have here. We have here a definition norm. So what is norm? Norm is kind of acronym, natural occurring radioactive material. So it's happened naturally. What I want you to know from this, and the next slide, yeah, that one. This is the activities that we have with norm. We have another definition for norm or another name, which is TE norm. The difference between norm and the TE norm is lies there. For example, sorry for this, I will share that. Okay. Here what we have here from norm at oil and gas, we have here, let's say, kind of well. This is a spot where oil and gas can be located. While having this spot, we have another layers from the underground earth. We have some sandstone, we have some rocks. This rocks contains radioactive material. That radioactive material, let's say, common material, which is uranium. But we don't have uranium itself. We have some radionuclei from decay chain like radium accumulated or attached with this sandstone. So these sandstones make an interaction with hydrocarbon. So it will be apart from them. So when we're doing drilling, we have, because we have human activities, we have technology enhanced radioactive material, because we now change the concentration from natural norm to man-made. So we have a change in activity. So we call it to norm. I think you're familiar with this. This is something related to normal contamination. When we are speaking for contamination, we have two kind of contamination, and I will go through the differentiate between them. But here, for example, we have when we the valve of pipes or oil and gas lines closed, the only type of radiation emits from radionuclides from norm is gamma only. But when it's open, now the risk or the ability to increase contamination will have three types, which are alpha, beta, gamma. But for decay chain, Most of them are alpha. Let's move to the another one. This is what I already talked about, something related to norm, where history of norm. Here, let's say some activities that related to norm in our job in oil and gas. We have here flow like Christmas tree. Here nearest the well, we have some kind like all this contaminated with norm, contain radioactive material. Here, let's see, this is kind of confined space under the bottom of that confined space. It contains lots of sludge. All that sludge, it contains norm, is radioactive. That's why we need to be away from radiation protection when dealing with this, and it needs lots of permission to do that. What we have here something we call scale. That scale accumulated inside the drilling pipes. This is big layer of scale. The type of scale itself, we will talk about it on the next slide. All of this contaminated with norm. For this is we call it ESBs. When we are doing drilling, we have something like this ESB, we call it electrical submersible pumps. It will shift the norm from underground. While doing this, the gas itself, while shifting the gas from underground, process to the ground up, it will be accumulated with norm. But when we trying to, let's say, get it in production, it contaminated with norm, so it will be affected the worker on the rig or the well. So what we have to decontaminate them, then inspect them, and then they will go to production again. Here some chemistry about norm. What we have here, we have barium sulfide and strontium and of course calcium. So here is the deal. Due to the chemistry of norm, which means due to decay chain, for example, natural uranium, we have one of its daughters, which is radium, radium 226. That element, because it's heavy element, it can substitute barium and strontium, also calcium, and then become or make that compound, radium sulfate. That what is accumulated inside those kind of drilling pipes. To remove them, we have some kind of techniques to remove all of this to become clean. If it will go to production, we have another way for them, which is going to manufacture steel to release them from the site, also from the oil gas company. Also, we have to decontaminate them to release them to the public, because it's according to regulation, we have a limit. Without this limit, we can't make that clearance. Here is some kind of sludge, and if you don't know the type of radiation detection, we have here American muscle Ludlam detector, and in the picture we are measuring by, this is, we call it pancake probe. We are measuring alpha and beta, and sometimes it measure gamma. But here for contamination, we're using this probe. There is another probe for gamma, but here we are using contamination. Uh, Here, okay, we are talking about this. This is also important. In general, we have two types of well. We have this one, conventional, and this is horizontal, this is modern. The main difference between those type of well related to norm, from any equipment from that conventional well, the concentration or the activity concentration for norm radionuclides is small. But this one, because we have its depth, so we have more norm. So the activity concentration that we got from lab results shows it's very, very high. This is what I talk about SPs, how it driven. This is driven by motor, and this is the intake, and we have a gas also separator to separate the gas from the rocks that contains norm. Uh, let's move to another slide. This is the decay chain. This is the uranium decay chain, and this is our nightmare with norm, radium 226. We have another isotope for radium, which is radium 228. This is come from thorium. TH, this one. So we have uranium 200, natural uranium 238, and its decay chain around 14 radionuclides. And the most ones that we found in lab results from gamma spectroscopy analysis, radium 226. And if you got in your lab results radium 228, that means that well contains thorium 232. Norm as any radioactive material because it comes from uranium, these radionuclides, so it emits alpha, beta, gamma, three of them. Most of them are alpha emitters. Here is about regulation or standards. For example, we have something we call exception levels. These levels, when you are trying to analyze in your lab results, you have these limits. But take care because you're supposed to comply with your nuclear regulator body. For example, in USA, they said some states the activity concentration for radium 226, they set it from 5 to 30 picocuro per gram. This is the activity concentration. Some countries, like let's say as UAE, regulated by FANAR, Federal Authority of Nuclear Regulation, they set the limit into only one becquerel per gram. So in UAE, it's only one. They said, mentioned in one sentence, each radionuclides from uranium decay chain should the limit is only one. But here, for example, we have lots of limits. For example, lead 210, it's zero point 0.2 becquerel per gram. So if you have a lab results according to FANAR and you got this, so it's not norm. But US or on some country, yeah, it's norm. So always follow or comply with your nuclear regulator body. When we starting our job in someone is talking or anyone can ask any question? Okay, you can ask, no worries.
Yeah, please
Eh,
proceed, Mr. Salah.
Okay, so how can we tell if we have norm because to have sampling and send it to lab results and then make a meeting to describe or to show if it's norm or not, something like that. So this process, it takes lots of time, especially for oil and gas owners. So according to your expert or as a radiation safety officer, when you are dealing with in the field, to say if it's norm or not, we have criteria, which is, first of all, you will take your device or detector and check the background. If the reading for the equipment or the tool that you are taking the readings, if twice the background, then normal maybe exist. But it is it need the clearance or not? That's something else, which is, for example, we have in Egypt, we have a dose rate criteria, which is 0.5 microsievert per hour. In some countries like USA, they have it 200 count per M for contamination. At UA, we have around 2 count per second, and the released criteria for some kind of like ADNOC. This is kind of oil and gas company in UA. It's around 5 count per second. I assume you know this all units. If you want to ask about these units, I am glad to share this also with you. This is kind of awareness about radiation biological effects to your body. So I think anyone I have to train him in on radiation protection. He have to be aware from this, so he will take care for himself. What we have here, we have, I will go too fast for this. We have two types of radiation biological effect, which is deterministic and stochastic. The key difference is the amount of radiation or threshold. The meaning of this, it depends on the amount of radiation that accumulated in your body. That's it. this is another information about this, but what I need from you to know about from this high lit and low lit. High lit is a definition. We call it linear energy transfer. We have it in basics. But for high lit, because it's very, very high, we have particles alpha and beta, and the norm or radionuclides or at norm, they emits alpha and beta mostly. They have also gamma, but most of them alpha and beta. So during alpha, and this is proton, not beta. So for highlight, we have alpha. We have alpha mentioned in our job. So take care about your contamination from alpha because it make a massive reactions in your body, nuclear reaction in your body. So take care from this alpha. Here, I think I go through this from periodic table. We have radium here. So radium can substitute all those elements. That's why I call radium because radium is kind of bone seekers. Why? Because calcium can accumulate it in your body, in which organ or tissue it's can accumulate in bone. So when calcium sulfate or sorry calcium carbonate reach your body in intake like from breathing or doing some activities from norm while you're eating or chewing a gum or something like this is something bad. I ask my technician not to do this, but what if so when you are dealing with norms with radium will substitute this and it can reach your bone. Now you have bone contains radioactive material, which is radium 226. So please take care when you are doing this radiation protection, when you are dealing with norm because of this nightmare. Yeah, we mentioned this also. This is about decay chain. This is in general about the radiological assessment. Before we started any tender, we have to prepare this and apply and in document and apply this to the nuclear regulator body in my country. And of course, we have to show all this procedure to the site owner. It's a kind of, let's say, like HSA plan. You have to make this. It included all things related to norm activities and how can you take precaution or take protection to avoid stuff from doing this beside environment, beside or the other one which is public. So we have three parameters here. Environment, this is the first. The second is the occupational or working. The last is the public because most of sites around them there is public and animals. So we have to take care from those. So how to protect them? You have to mention this in your assessment. This is also about details about that topic. For example, this is I designed this for one of my project at UA, offshore UA, at one of this island, which is Arizona. I did this. Here, now we are in business. This is a normal procedure, how it works. So first it starts with identifying norm. For example, the site owner have a tender and he publish it on his site. To apply this for that tender, first of all, if it norm, we will go to see the site. I will visit the site. I will identify the norm. I will identify the quantity of norm. Then I will measure to detect which area is high, which equipment is low, something like that. Then I will make a plan to decontaminate, which is suitable techniques for decontamination. Can I use chemical? Can I use sandblasting if it allowed? Can I use water jetting? Something like this techniques. Then my plan after finish decontamination, how can I collect this waste and handling this waste because waste handling is very, very important because we have lots of type of waste with norm. We have a scale, we have a sludge beside contaminated BBE that we used for normal decontamination. We have to take care for of all of this. After that, we will store it in a temporary area. We will call it temporary storage. until we have an action or to move the next step, which is final disposal facilities. We have a suitable disposal facilities for norm. According to IEA, let's say they classified it as very low waste. But when I got some lab results from that waste, I found it's not very low. It's low. So according to this, you can design your final disposal facility. Here we have some, let's say in general, some activities. This is norm yard. This is the equipment I have to detect. This is the showroom after I finished. This is how it looks like after finishing. Here I used chemical. This is we call it pumps. This is HP pump. We use it for water, for pumping water to from and to the well. This is a separator after cleaning. So you have first take the readings. If it high, then go to decontaminated. After decontamination, take the reading again. If it below the limit, now it's cool. You can show it to the owner for releasing from your site. So the first step is to say if it norm by legal, not by your expertise or experience. First, sampling. You will go to the site and take samples and then send them to the lab results. Sorry, for the lab spectroscopy or lab analysis. We're using high purity germanium detector at the lab for detecting those radionuclides from natural occurring radioactive material and check the activity concentration or specific activity. This is
Mr. Sala, if I may interrupt, for the sake of time, please, maybe if you could hasten a little bit, thank you.
okay, I will. Okay. For example, this is a lab. This is high purity germanium detector. This is a lab results from one of my sampling campaign. Let's say for here. This is very important as a radiation physics specialist. You're supposed to know this. What we have here, for example, we have radium 226. This specific activity is around 1. So it's norm. If it's less, it's not norm. But if it like this, so then it means this norm. This is another lab results we have here around 0.56. So it's less than 1. But we have another radionuclides, which is lead 210. We said from exemption level about IAEA regulation or nuclear regulation body, 0.2. This is higher than the limit. Then it's norm. The second thing is classification your area. Before you start the job, we have 3 type of areas like zones. When we are dealing in oil and gas, we have lots of, for example, toxic gases like H2S. We have zones, zone 0 and zone 1 like USA. We have the same at norm. When you are dealing with radiation protection, we have 3 areas. Public, out of your fence. Supervised area, it's after the fence, your yard fence. The last area, which is controlled area, sorry, controlled areas, this is for decontamination. How can you tell or classify them? Classifying them according to those rate or those rate produced from this area. For example, for public, it's less than 1 millisievert per year. So anyone in this area shouldn't exceed this limit. Supervised area, for example, at USA, they said it's 10th value of annual occupational dose limit, which is 1/10 multiplied by 20, it will 2 microsievert or 2 millisievert. That's it for supervised area. But at UA, they said it 2.5 millisievert. About control, it will be from, let's say, 2 to 6. This is higher than this, then this is restricted, totally restricted area. You don't allow to be there because they maybe have some kind of unartificial sources, so you will not be allowed to be there. This is about our areas. The decontamination. To decontaminate norm, we have, as I said, lots of techniques. High pressure water blasting. We have chemical decontamination. We have drain reaming. We have vacuum. In this, I would say if you are beginner, this is the best choice. This one is doing blasting. But for high pressure, we have start from let's say 150 bar until reach more than 2000 bars. and the system could be closed. So to avoid any contamination or dust, something like that, because this is contaminated dust. So to avoid this from air contamination, you have to make it closed. Here for chemical decontamination, we can use some kind of material, for example, acids, to make the layer between the scale and the surface, the inert surface of the draining pipes weak. Then by applying water jetting, then we can remove norm scale. This is some types of equipment that we have or I have in my yard. For this is example, this is drain pipes. Here, this is SPs, SPs also. We have here cables that we are using in fracking. This is cable that running the ASB motor. It's also contaminated by norm. Here in onshore, okay, we have this sucker rods. These rods are connected to each other with onshore. For example, they're here. We have them from there to there and also in the downhole. This is also contaminated by norm. It need to be decontaminated like that. We have some valves like this. We have also some filters like strainers. All this accumulated by norm. We have separators. It's also from at oil and gas, when especially in gas section, we have those separators to separate oil and water and gas. So it's also used to be accumulated by norm, need also to be decontaminated. This is how it works. So we are talking about this is also about radiation protection or the waste itself. Yeah, we have something else which is you need to be aware of, which is mercury. I got some results when we're doing gamma spectroscopy. We are tracking or tracing those radionuclides like radium or radon gas. I will talk later about radon gas. But some companies didn't don't be aware about mercury. This is toxic element. How to can we have some, let's say, result from this one? How can you detect it? You can detect it from chemical or chemical analysis. So you have to make two type of lab analysis, one for gamma to detect these radionuclides, and one for chemistry to see this the concentration of mercury, because it's very very it's not our core, because it's not radiation, but take care from this one. Here how the norm accumulated. This is chemistry also. This is how it looks like, scale layer after decontamination from inside. Here evaporation bond, we using this evaporation bond for kind of waste handling. What we do, after we decontamination, we have produced water. We let it and the sun will hit it, and then we will collect it, the residuals. This residual all contains more. We have another technique like vacuum. We have, this is evaporation bond. This is vacuum cleaner like separator. We separated, we got the norm waste like sludge. We will fill it in this machine. It will be separated. We have two phases or three phases. This is an advanced techniques. Vacuum dry. What will happen here? It will separated oil from water, but having around, let's say, 100 degrees. So water will be evaporated. So what we have there, we have the solid waste, which is norm, and the liquid oil. By having a proper it's not melting, by have a boiling like around this 300 degrees, we can separate oil from the sludge or the norm. So we have separated this. So when we collected that norm sludge, and we stage it in a parallel till to check the next move. This is how it looks like. Also, this filter contaminated. This is for waste handling. This is another type of radioactive or artificial, something like that, not for norm. This is incinerator. Yeah, this is important. After you finish, let's say you have around the big stuff from PPE. So what you will do with this PPE? Should we burn them? In old days, they used to burn them, but they figure out it contains some radioactive concentration. So we use this incinerator only for PPE. like disposed coverall, gloves.
Nimesikia hata sisikii kitu na kuna kitu nilikuwa nataka contribute hapo.
Sorry for this.
Just a minute, please.
Yeah,
Mute.
for surface contamination, you need to read this. We have those two limits. So before you release this is your criteria. For alpha and beta, this is yours. Sorry, for beta and gamma, but for alpha, this. So I think the next move is transportation because it's very, very important when you are dealing, which is labeling your radioactive. What we have here, I will show you this label. As a radiation physics specialist, you have to mention this first content. For example, radium plus, it means it coming from norm, or the active or radioactive radium is inside this container or package is the activity coming from radium. The activity you have to mention, how to can mention or calculate your activity in a brief. For example, if you have a drum contains around 200 gram of sludge, kilogram of sludge. So this 200 multiplied by the activity concentration that you got from your lab results, now you got the total activity. What about the transparent index? Transparent index only for radioactive label, YOLO 2 and YOLO 3. But for white, we don't have transparent index. How can you calculate that transparent index? I will.
Mr. Salah,
Yes, ma'am.
if I may interrupt, for the sake of time, please, if you don't mind, maybe you could wind up in the next 2 minutes, and we really appreciate these slides because they are quite informative, extremely informative. Thank you.
Thank you, ma'am. Thank you, ma'am. Okay, I will. So can I finish now, or you want me to go through fast for the next few slides?
In the next 1 minute, if it's
Okay.
okay with you.
After transportation, we have some labels for transportation according to regulation. This is your criteria for first label. Okay. This is also important. This is summarized for the radioactive labels. This is labeling radioactive. Okay. For this. Okay. This is advanced. This is something related to multiplication factor for the container or the something that you are, let's say, ship your radioactive material. Lots of about this is norm west type of west. As we said, we have here we have this we have I will not go through for all of this west, but the idea after you collected the west, you have to handle it first to minimize the amount of waste. After this, we will send it to the final disposal facility. We have more than one of final disposal facility, but according to norm, what type we have? We have most of them in old sites. We have landfill sites, and it's also, as I mentioned, classified by IAEA as very low level of waste. This is in old waste. The criteria between, or the differentiation between very low level of waste and low level of waste is active in activity concentration. So you will make sampling to check for that type, which is low level waste. Your limits will between 100 becquerel per gram until, let's say, 400 becquerel per gram. If your sampling shows this, then I think your low level waste facility will be great. If not, then landfill will be accepted. The main difference between them also in the between the two type of waste is in radioactivity long lifetime. For example, radium, it's around 1,600 years old. So we have activity and we have T-half. When you are talking about your waste, you have to take care about those two parameters. Something else which is related to waste handling. For example, in nuclear reactor, we have waste that need to be shielding because it produces lots of heat. This is another type of waste. We don't care about it because it needs deep or depth to disposal. Comparing with norm, what we have here, we have norm, we have something like that. But when you design your facility, please make sure you have shaded area. Keep it away from rainwater because when water can reach the norm drum, it can damage, and then we have a spread of contamination. It can reach underground water and it can be dissolved by water, and then you can, or the public can drink this water. So we have a spread of contamination. So when you design this facility, you have to be away from all of these scenarios. This is more about that. We have extra for that type of waste at oil and gas in Egypt. I have some artificial waste, for example, like iridium 198 that we're using in gamma camera, and also cobalt 60. I designed a bunker and used to take leakage source and put it them. This is not normal, but you can use that type of facilities or final disposal facilities to waste to store that kind of waste. This is kind of a sketch or something like how it works. For example, this is very, very great. The idea is try to, let's say, separate water or underground water from that waste, because water always it's nightmare for me when design any facility. I have to put something like a material like this is concrete, and another material like bonatile to separate water. Even water can't reach this, because when it reach, this is damage. For now, that's it. Thank you.
Thank you very
Yeah.
much.
Any question, please? I am happy to answer any question.
Yeah, we really appreciate your presentation. Actually, NOM is a new area, especially for us in Kenya, which we are really looking into controlling with regard to, for instance, mining. There is a NOM waste that is generated, but for the longest time, it was not being seen as NOM waste and being of radiological risk. So your talk could not have come at a better time. I don't know if there's one person with there's one question that Mr. Salah can handle because of time we go to the next presenter. Just one question for Mr. Salah.
Maybe, Margaret, if we give the floor to Dr. Valeria, because she's been waiting for her presentation, and I think we're a little bit behind the schedule.
All right. Thank you very much, Florencia. If you have any question for Mr. Salah, please note them down and we'll forward them to him to answer. Mr. Salah, kindly pull down your slides. Mr. Salah, please pull down your slides. And if you would like to ask Mr. Salah a question directly, stay until the end of our presentations and we'll give you a chance to ask Mr. Salah the questions. Also, Mr. Salah, we would really appreciate if you could share with us your slides. My students can also benefit a lot from them. The information is quite informative. The information is quite important. Ms. Valeria, welcome, and kindly share your slides.
Thank you, Margaret. Do you see my screen?
Yes.
Perfect. Hi, everyone. I'll try to keep it short and sweet, and we'll be happy to answer the questions at the end together with Dr. Sala. My topic is slightly different from what was presented right now, and actually I'm going to talk about mathematical modeling and Monte Carlo tools for radiation transport. When we're talking about radiation transport, basically, I just want to make sure that we avoid the confusion. It's not the transport of radioactive material. It is actually of penetration of radiation in matter, which is quite common, quite usual, and can be applied for different scenarios, different uses, different applications. I would like to thank everyone for a very nice introduction. And as I mentioned earlier, I just retired from the IAEA literally last week, so I'm still in the transition mode. But I have experience both in academia, in industry, and in international organization, and would be happy to help and assist and advise whoever has questions regarding these different places for work, etc., etc. So back to the topic, Monte Carlo tools and penetration of radiation through matter. How can we use it and why do we want to use it? There are a lot of applications for that. One of the specific one I'm going to talk about today is radiation dosimetry, even though it can be applied for a lot of other applications. Very often when you have radioactive material or you have some kind of radiation producing machine, for example, a particle accelerator, you irradiate different products. Sometimes it happens intentionally. You want to irradiate it to change their properties, to sterilize them, to do this or that. Sometimes it's undesired, and then you want to shield, vice versa. And to help you predict what kind of doses would be in different parts of the product or in different parts of the shielding, or what kind of particles are going to penetrate, what would be their flux, what would be their energy, what would be their distribution, etc., etc., how much energy would be deposited in the material. All this, of course, we can measure experimentally, but at the same time, it always helps to do these simulations and to get a feeling of what we are expecting, or how big this shielding is going to be, or how high the dose would be from this cobalt source, for example, or from this electron accelerator if you have certain beam parameters. So while in dosimetry, there are, of course, very nice tools to measure. There are a lot of different dosimeters depending on which dose you're talking about. You also want to use your computational tools, your in silico modeling as much as possible, just to save time and to make your life easier. Another advantage of in silico methods is that very often when you don't have a laboratory, when you don't have expensive equipment to do experimental work and experimental measuring, you can very easily, in many cases, do simulations. And this is an excellent opportunity for a lot of participants from developing countries who very often come to us when I was at the IEA and would say, okay, we cannot do this and we cannot do that. However, there is a lot that can be done just using computers. So specifically, as I said, I'm going to talk about dosimetry and I'm going to talk about absorbed dose. And here you can see several examples of products that we routinely used for this kind of work. So as you might know, a lot of food is irradiated in many countries, a lot of spices, a lot of fruits, vegetables. In many countries, it's allowed to irradiate meat and fish, etc., etc. So for different fruits you want to, and vegetables and products, you want to know what is the dose. Especially if you irradiate, let's say, a big box, you want to know what is the dose distribution. You want to make sure that the front of the box, which is getting, let's say, the most dose, is not significantly higher than the back of the box. You want to ensure that the dose uniformity ratio, the distribution of doses, remains within the limits that you would like to have. Same is true for medical devices. You see a syringe here in the middle, and this is a very common example of what has been irradiated to sterilize it. Before you inject something into a patient, before you put something into patient's body. Another example on the left actually is just using some prosthesis and artificial implants for hips, etc., etc. Before you put something into a patient, you want to make sure it's sterile. And if in case of metal prosthesis as shown here, you can thermally sterilize it with polymer materials like this syringe. You cannot heat it up to the temperatures high enough to sterilize it. So radiation sterilization is very common. So when we're talking about the dose that all these products receive, we actually need to have some kind of common ground, because the dose, the actual dose, really depends on what kind of material you radiate. It depends on its chemical composition, and it would be different for metal and plastic and the fruit shown here. So that's why we typically have some reference point when we say everything we measure is referred to absorbed dose in water, if this material is made of water, and then we do the adjustments. The simulation, the Monte Carlo simulation, as I mentioned earlier, are used in a lot of different applications. Dose distribution, the product for this, fruits and vegetables and meat and fish and medical products and drugs and cosmetics, etc., etc. It's often done for your IQ or QPQ, for the processing, when you want to do some quality control and basically confirm that these doses are within the limit. When you try to characterize a new dosimeter, especially if you are developing a novel type of dosimeter and you want to make sure that these new types of dosimeters actually measure what they're supposed to measure. Very often it's used for shielding. When you are trying to build, let's say, a new facility and you want to create some kind of a maze and you want to make sure that there is no radiation outside the maze, or if you are developing a new type of transport container, again, you need to know what kind of, how thick your material should be to ensure safety of people around it, and a lot of other applications. So I'm sure many of you have heard the word Monte Carlo. What really is a Monte Carlo? And to answer this question, I put together a very simple cartoon, a very simple exercise showing you the basic idea behind the Monte Carlo methods. And in fact, when you say Monte Carlo, it's just a common technique which can be applied to different areas, not only in nuclear, not only in physics, but it can be applied to a lot of processes in a lot of different sciences. In general, basically, it's a technique when you put a big number of random processes and basically governed by a particular law, physics or non-physics, doesn't matter. And we will see right now how the number of these data points increases the accuracy of your simulation. So let's assume a simple square with the side of 2 centimeters. So you know that the area of this square would be 2 by 2, which is 4. And inside this square, there is a circle with a radius of 1 centimeter. And this, the area of the circle would be pi r squared, which is pi times 1 squared, or just pi. So if we calculate the ratio of the areas, the equation shown on the bottom, that would be the ratio of the area of the circle divided by the area of the square, which is going to be pi for the circle divided by 4. So we know that if we start shooting the dots randomly in this circle, in this square, and then we just see how many of them end up in the circle and how many of them end up totally in the square. Comparing the number of these dots, imagine I have darts and I just keep shooting and shooting and shooting, and some of them end up somewhere in the corners, some of them end up in the center, some of them end up basically everywhere in the square. Then just calculating the ratio of the points inside the circle to the total number of points, I can very accurately calculate pi. We all know from physics that pi should be about 3.14. Let's check it. So if I run my Monte Carlo simulations And if I end up with a certain number of points, if I end up with a certain number of points, here I start with 1,000. 1,000 points, you see that some dots are shown as green. This is the top right square, and some points are shown as red. And the pi happens to be 3.18 if I just divide this number of points, and it's not very accurate. So if I increase the number of points, now you can see that the picture becomes more dense. Now I have 10,000 samples, 10,000 projectiles. Now the pi is closer, 3.1434. I increase it even more, 10 to the 7th power. Now a number of projectiles is 10 million, and the pi gets closer and closer to what we expect it to be. In the same analogy, what we do with radiation transport is we basically launch particles. So for example, we launch a photon with a certain energy, and then we see what where it would end up, how much energy it would carry, etc., etc. Photon, electron, neutron, doesn't matter. So the whole idea of Monte Carlo, the essence of Monte Carlo, is we start with some kind of algorithmic method. We start with whatever is our process, whatever we want to measure. Then we use some kind of theoretical laws and models. For example, we define if you have an electron, then it should scatter from a nucleus according to this particular laws. Or if you have a photon, then it should travel this way and that way. So all the laws that govern the interaction of particles with matter, we put into the core of physics. And then our outcome would be the calculated quantity. For example, how many electrons or photons or neutrons end up outside the maze or outside the box, and then what would be their energy, what would be their momentum, what would be the direction of these particles, from which you can calculate what is the dose, what is the flux, etc., etc. So there are a lot of different tools to do that, and there are a lot of packages available outside available basically worldwide. I am going to talk about 3 particular packages here, and I will outline their pros and cons. In reality, of course, as I said, there are many more. They all have their own pros, cons, they all have their drawbacks. Actually, our section has been preparing a publication which goes over what kind of tools are available, and it should be published soon, so I would be happy to share it with all of you. But for today's purpose, I'm going to focus on 3 of them only, and one of them is GANT4, which is a package pretty common, pretty popular, primarily for high energy physics. However, it can be used for low energy as well. Another package is called MCMP. Again, there are different versions for them. And the last one is Ray Expert. So if you think about GANT, that's probably the most accessible one. Everyone can download it. It's free. You don't have to license it. You don't have to pay for it. There are no constraints. Everybody can use it. MCMP, on the other hand, it's free if you are in academia, if you are a student, or use it for educational purposes. However, if you try to use it commercially, there is a fee associated with it. Moreover, this package is coming from the United States, and there are some export control regulations. So as a foreigner, you can use it, but you have to get a license to get the files. Finally, Ray Expert is a commercial package. It's very user-friendly, very easy to use. However, you have to pay for its use. So again, I tried to pick 3 different packages. One is very accessible, a little bit harder to learn. One is very easy to learn, but you have to pay for it, and something in between. As you can see, there are different versions there. So the top line shows you different versions for each packages, and believe me, they do update them very often, and there are some new things coming for different packages. These are just some properties of the packages and how fast they're going to work. As I mentioned earlier, the more particles you have, the more probes you have, the more accurate your answer is. So you want to make sure that you're running enough particles. And to do that, either you have to use a lot of processors, or to run it in the cloud, or do some parallel processing, or run for a very long time. And I'll talk more about it a little bit later. So here is an example of how the outcome of the simulations looks. So you start with the electron beam incident on some titanium window. So this is an example for a particle accelerator. And once you have this titanium window, and here are just some parameters for your window, its dimensions, it's 40 micron thick, its density is 4.5 grams per cubic centimeter, and about 80 centimeters away from this window, there is a block of polystyrene polymer, again with some properties. And you can see how your electrons before the window, above the window, they all go nice and uniformly and all go down. But then they start to scatter because of the interaction between these electrons with titanium. You also see some green arrows in addition to the red ones, and those are the photons, the Bremsstrahlung photons, generated as a result of this interaction. So when you try to look at the dose map in this polystyrene block, you would see that it depends a lot on what kind of physics models you use, what is your mapping, and how do you analyze your data. So when you are trying to use GANT, and again, please check it out, this software has been developed in CERN, in a big laboratory in Europe. And again, it's available for free. You can download the files, you can download, there are a lot of tutorials. It's not a very user-friendly software, but once you master it, you can do a lot of amazing things. You put your basic geometry in the GANT, you describe the system, you need to show that here is my titanium plate, here is my polymer block. You need to include your physics. You need to say what kind of laws exist in this universe, what are my materials, and what is my detector, and then you run the code. So sounds pretty simple. In reality, when you are running the code, it looks like a lot of files, and that's why I said this particular package, while very powerful, very good, it's not extremely user-friendly. So don't expect to learn it one day. It would take some time. This is the typical file for the code. However, once you run it, you're gonna end up with the image shown here, where again you see these yellow lines show the titanium plate at the top. In the middle, the blue lines represent the styrofoam block. The red ones are showing your particles, and the green ones. MCMP kind of existing, these all codes work more or less the same. So you create your mini universe where you say, okay, I don't model my whole lab. I don't model my my tables and all the equipment and all the accelerator, all the sources. I just have a very simple setup. Here is your titanium plate shown as blue, dark blue on the top, and your polymer block is shown as green. Rectangular prism, and again you just say my particles, my electrons come down along the z-axis, and then they hit the titanium plate, and then they start scattering around. This is your input file for MCMP. It's not that complicated, but yes, there are a lot of physics, there are a lot of physics models, there is geometry as well. And once you have your model set up and your physics set up, then you just run it for whatever the number of particles, and then again you get the result. Ray Expert, even more user-friendly, because here now all you need to do is to fill out the boxes. You have a GUI, graphical user interface, and you can see that on the left here it says titanium. This is where you type in your material, your thicknesses, your dimensions, and then you press the button. So the difference between this prompt, this window, and MCMP or GANT is huge. So, but yes, you have to pay for this simplicity. So the general comparison, if you think about, again, compare several versions, how many particles do you get, what is your mesh resolution and processors, and what kind of physics you use. In reality, there is not that much difference. So these all packages, they more or less do the same thing, because physics remains the same no matter what you do. There are slight differences because of the resolution, because of how many particles you run, and because the libraries are slightly different. The output files typically use typically look like this. So just bunch of numbers that you need to convert into some visual. And if we do convert them, here I was trying to compare several packages and the experimental curves. So you can see that GANT, MCMP, and Ray Expert, blue, red, and black, they are actually in a pretty good agreement for this particular exercise. If you look at the gray dots, you will see that these are the experimental values. There is some discrepancy, especially at the peak, but other than that, it's a pretty good agreement and it's a pretty good fit. So I hope that this simple exercise, which I used to compare these three packages, persuades you that they all work, they're all good, and I encourage all of you to think about, for whatever work you're doing, what kind of packages can you use, what kind of what is available out there, and how would it help you with your work, with your research, with your whatever you're doing, working in university, working in a hospital, working in maybe for a private company, but how could computational tools help you? What can you do with them? So in conclusion, basically, I just wanted to reiterate one more time that there are a lot of different packages that exist. And they're all different. And you need to think about, if you decide to go and try to do some modeling, what do you want, how do you want to invest into? Do you want to invest your time, get a free package, but basically learn it and learn how to run it? Do you want to invest as money and just buy a tailored commercial package? Remember that while commercial packages are expensive, they're very good in terms of user friendliness. However, on the other hand, when you're just pushing the button, sometimes you can put in some wrong input, and then the output is going to be pretty misleading as well. So if you are using a commercial package, be careful, because it is a black box. And if you do garbage in, there will be garbage out. So from my personal experience, especially for younger people, I definitely recommend to go for free software, invest some time, learn how to use these packages, learn how to run these packages. There are a lot of schools that are organized by the IAEA and by some other groups that help learn. And I encourage you to check it out and ask around and see if there is an opportunity for that. So I hope that was pretty. I know it was brief, but I hope that it was relatively clear. And I will be happy to answer more questions. And I hope that you will be able to use it in your work, and it will help you. Thank you.
Thank you very much, Ms. Valeria, for that very informative presentation about Monte Carlo simulations. As students, I see our students talking about Monte Carlo simulations. So if Kenyatta University students are here, I believe you've learned a lot from Ms. Valeria. So you know exactly how you're supposed to go about it. Monte Carlo simulation, GNT4, those are terms that I hear our students at the university, postgraduate students at the university mentioning. So today we thank you very much for that presentation. And with that, we come to the end of the very informative presentation, both of them very applicable to students at the university, to the regulator, norm regulator, those who want to do simulation. We appreciate that. And now I'll pass over the mic to Florencia for the question and answer session. Thank you so much.
Thank you very much, Margaret. Thank you very much to Mrs. Valeria and Mr. Shala for the great presentations you delivered today. I see we have some questions in the chat. I'll just try to speed up on this because I know that we are a little bit behind the. We have a question from Kawula. I think Kawula is asking, thank you very much for this insightful presentation and the comprehensive information shared. I would like to ask, what are the current considerations on the loss of effective and widely adopted methods for the safe management and disposal of norm waste in the oil and gas sector? Please, Mrs. Shala, if you can comment on that, we'll appreciate things. Mr. Shala, are you still with us? Maybe he's having some challenges with the microphone, Margaret.
Yeah,
Mr.
hello.
Shala.
Salah, yeah,
Yes,
Salah.
please.
Yeah.
Salah, sorry, Mr. Salah. I'm sorry for the mispronunciation. Um, should I read the question for you again?
Yes, please, ma'am.
Kahula is asking, Kahula would like to ask about the current considerations of the most effective and widely adopted methods for the safe management and disposal of norm waste in the oil and gas sector.
So I am afraid to say I didn't, let's say, know exactly what he is talking about. He is talking about time management or loss of time management or something like that. So can he?
Safe management and disposal methods.
Yeah, it's very, very important. For example, let's say if we have around in all the site, like I visited in Iraq, around 100 drilling pipes. This is pipes are accumulated with norm, and they want to release it from the site and sell it to the manufacturer steel. Can they do this? No, they can't. First of all, they have to contaminate them. To do this, they need radiation protection. They need to comply with nuclear regulator body for clearance. That's why they need us. So, for example, I will mention something related to financial or cost. Those 100 pipes can cost around $30 million. So to sell them to manufacture steel and the owner gain this money or that money, he have, let's say, obstacle or something, a challenge, which is he have to decontaminate them. That's why he need us. So to collect that money, he's supposed to need radiation protection, let's management inside his own facility, or he can manage it through any services company provided that technology or that services. So this is the answer. Or you wanna ask another one, or you didn't get the correct answer or something like that. I am happy to share it with you. No worries.
I think the comment was very clear on the explanation you give also about the financial status and how everything is related. We have an additional question from Kennedy. Thank you, Mr. Mohammed Shala, for your presentation. I would like to know the radiation levels of oil and gas or filling stations and how are the stations attendants are protected. I mean, in terms of the year and the equipment while they do the oil and gas process.
Yeah, in process, we have in oil and gas, as I mentioned, we have zones. When you are visiting or making, let's just say, walking through inside your area as an oil and gas representative body, we have restricted area. We can post or can put our restricted labels or signs according to activity. For example, as I mentioned, we have in area classification, it classified according or based on absorbed dose rate. So you can say if it this area contaminated or not. You have lots of devices to check. First of all, you have to check by your gamma spectroscopy. Sorry, your gamma probe. For example, we have a famous brand like TerraCirco. We have a norm kit. This one, let's say we have two types of them. We have one can work in zone 0, which is labeled by IS. This is a mark like intrinsically safety. This can works in zone zeros. So when you are measuring the dose rate, if it 1 microsievert per hour, then that means this area is contaminated. What if it less than this? So according to your regulator body, Less than 0.5 or double background, then no need for protection, and you can move. Only the protection at oil and gas, or the common PPE at oil and gas company, like helmet and wearing your gloves. But if the readings is very very high, like comparing with 6 microsievert per hour, those rate something like that, in that case you will detect what type of source emits from this area. For example, if it contaminated air, then mask is must. Because we have here radioactive air, it means we have some small residual of alpha particles, emitters, especially also for some places like confined space, because this places is very, very, let's say, before shutdown, we can close them for a long of time. And when we open it while doing shutdown maintenance or something like that, we have some trapped radon. This radon is radioactive gas. That's why you have to wear your protective face mask. When you are
Okay.
doing the contamination inside this confined space, you have to wear this. We have kind of detectors for tracing this air population, especially tracing this radon gas. Also, when you have a package, closed package, for example, I am I made a transportation from my storage to the final disposal. When open the container, keep it for a while, so we can release this gas. After this, we can do in our activity. So
Wonderful.
Yeah,
always keep your
Florentia.
Yes, okay. Sorry, Mr. Shalaf, if you have concluded, we need to jump to the next question from the participants.
Yeah, Florentia, just to clarify about that question Mr. Salah has answered, maybe he did not get it quite correctly. Uh, the, 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 the question was about radiation levels at filling stations. Do we expect to have radiation at filling stations where we go to fuel our cars?
No, absolutely not, because anything released from the site supposed to be conduct a radiological survey to check if it, let's say, for example, if it doubles the background, then it's contaminated with norm. We can't shift it outside. Only for production, for like what you are filling in your car by gas. No, it's not. But it have some lower residuals. Even drinking water sometimes contains radium, but it's always below the limit. It's not toxic. It's not radioactive. Like, let's say banana. You are eating a banana. This is radioactive. So is it cool or for you, or it's dangerous? It's natural. Something you don't have to worry about that. So anything moved out the oil and gas site, it's, let's say, legally or by nuclear regulator, it's allowed for public. So no worries about this.
Okay,
Okay.
thank you so much.
Thank you so much, Mr. Shalaf. So we have a question from Ayman. If you would like to open your mic, please. If you can unmute yourself and please introduce yourself, and then you can make your question.
Okay, thank you very much. Can you hear me?
Yes,
Am I
we hear you
unmuted?
well.
All right. Good day, everyone. Yeah, connecting from Nigeria. It's a great pleasure to be here. It was quite an interesting presentation from Mr. Mohammed Salah, though I came in a bit late when he was almost rounding up, and I saw he was talking about Norm, the second presenter from Monte Carlo. They were both an amazing presentation. So my question here is related to the transport of the Norm. I wanted to know if there's a particular company that are responsible for transportation of the norm, because currently myself and my team, we're currently working on on an abstract related to non-transportation. So, want to know if there's any how we can, if there's any particular company that handles the transportation of the norm, and how we could get access to some information on how they go about the transportation and the safety during the when the on the during the process of the transportation of the radioactive materials from the site to a particular location. I don't know if I'm clear.
Yeah,
Yes, I think you're clear. And maybe any of the speakers also, Mrs.
Yes,
Valeria,
thank
she
you
can
so much.
reply, or Mr. Mohammed as well. Thank you.
yeah, thank you, Ayman. Yeah, it's totally clear. For nuclear regulation body is a man who is regulated this transportation. For example, to transport norm from site to site inside the oil and gas company, we don't have any license for transportation because it's still inside the premises of oil and gas company. If it released to the public, it means we engage in the public road, something like this, with having radioactive material. So yes, you're supposed to apply for license. You will mention in your license that you will apply nuclear transportation packages. For example, for norm, when as a radiation safety officer at the site, it's not your job to transport norm package from the site to the final disposal facility. It's another company will do this. After license company, after they gain the license, they can moderate this activities. Your job as a radiation safety officer, you will make sure taking the dose rate for the package before transported or loaded on the cargo. You will make, as I mentioned, some calculation to calculate the total activity for the whole package. You will mention the type of waste. You will mention also the transport index if it applicable. After you make sure of this, you will collect this file. You will apply this also to your nuclear regulator body. Then the shipper, which is the license company that are dealing with transportation of radioactive, they will collect the package and they will apply papers related to their company to the nuclear regulator body in your country. After they, let's say, unloaded the package for the third party, which is final disposal facility owner, he is also licensed for he got or he gained his license from the nuclear regulator body. He will make paperwork and he will also apply it for your nuclear regulator body. From this, we have, let's say, kind of control on the package. We know where it come from, who transported, where it reach. Now we know all things related to that package. Thank you, Ayman.
Thank you very much for
Thank you
your
so much.
answer.
Thank you. Sorry, I also want if I can get his contact, Mr. Salah, and because I also want to know more about the shipment company. I don't know if I can get his contacts to for further communication with him. Thank you.
Thank you. Maybe if you can do us a favor, Mr. Mohammed, to drop your email and information contact on the chat, that'll be great that people can get connected to you. Same for Mrs. Valeria, Dr. Valeria as well, if it would be possible to have your contact there on the chat.
Absolutely. I also can add just very quickly a few words about licensing and using simulations. So when I was working for a private company in the US, we did apply for a number of licenses to possess radioactive material, to produce radioactive material, to transport it, etc., etc. And simulations played very important role. So basically you have to prove, for example, that we're going to produce a certain amount and no more than that. So to confirm how much you're going to produce, and you don't have a license yet, so you cannot experimentally do it and say, look, we produce that much. So to do that, you definitely start with simulations and you say, this is exactly what we're going to do. This is exactly how much we're going to make. Same for shooting. So when we were constructing certain facilities, we showed that, okay, if we have 1 meter of concrete and 40 centimeters of lead, for example, then even if we have the maximum activity, it will not exceed certain values. So yeah, there are a lot of various applications. Thank you.
Thank you so much for your detailed explanation and also giving the overview of the Western side. It's important to connect practices across the world. Please, if anyone has additional questions, we have an additional question from Kahula. Thank you for your presentation. It was full of information. My question, I'm doing a master's in radiation protection safety and nuclear engineering. Do you think I should learn Monte Carlo methods or Gen 4? Are there any sites that can help me to learn from the scratch? Thank you. That's for you, Mrs. Valeria.
Sure, I think absolutely, and I think the comment that I just gave about nuclear safety and basically, sorry, not nuclear safety, about radiation protection, because we did have, when we did experiments, we did have to predict what would be the dose, let's say, on the surface of the bunker or on the surface of a particular shooting area. So yes, I believe that that would be very very good fit. So if I were a radiation safety officer, I would definitely want to know some Monte Carlo. So yes, I advise you to do that. And as I said, there are a lot of opportunities. There are a lot of definitely for Gen 4, there is a lot of material which is available online. All you need to do is just Google Gen 4 and you will see a lot of distribution documents. There are a lot of tutorials and manuals. I also encourage you to look into some schools and programs that IAEA supports for radiation safety, and I will be happy to provide this information separately, so you can distribute it with the participants. Yep.
Thank you so much. We will be very happy to know that information. I think annually or consecutively during the year, I organizes in conjunction some schools with ICTP in Trieste.
Exactly. Yeah. In Trieste,
So
we run this pretty often.
So for those participants, you can also have the chance. I mean, they provide some available grants for participants on site, or sometimes there are also slots for virtual participation, and then you get the certificate at the end of the training, right? So if anyone has any additional questions, please feel free to do it because we are about to conclude this webinar. It's been very informative in this session, and we have now the email contacts of Dr. Valeria. Please take a note of that, and also from Mr. Mohammed. So as we are approaching today, we want to thank all the colleagues, friends, and participants for today's session, and we want to extend our heartfelt thanks to each of you for joining us using this third edition of the Radiation Protection webinar series. We had the privilege of hearing from outstanding speakers who brought deep clarity and innovation to our understanding of radiation protection, from the industry realities of norm on oils and gas to the transformative potentials of algorithms and modeling tools in radiation protection. Thank you very much for everyone who made this webinar possible. And as we move forward, let's carry with us the spirit of this webinar, one of curiosity, cooperation, and commitment. Last but not least, we would like to invite our colleague Lancina. He's the founder and main coordinator of Newcomers for Nuclear Initiative, to provide some few remarks about this session. So thank you, Lancina. Over to you. And please, one last comment. The slides will be shared with all the participants after the event, as well as the recording. So thank you very much, Lancina. Over to you.
Thank you so much, Florence, for the speech. I would like to thank the presenter, the moderator, Margaret, and the team. Thank you so much for all. I would like to note that it was a very, very important session. I start my speech. Good morning, good afternoon, good evening where you are. Dear members of the U network on radio protection and nuclear safety and the group Women in Nuclear Innovation UNI of Women in Nuclear Global Network. I would like to thank you for involving my modest person in this activity of your collaborative, dynamic, and inclusive platform for learning, networking, and professional growth. You initiated, implemented, implemented it to shape the future of radiation protection and nuclear safety in Africa and in the world. What is exciting is that you prepare your future from teaching and guidance, not to yourself directly. It is an action of solidarity, humanism, and strengthening human potential. It is to be welcomed at its true value. Indeed, our continent is full of health, and it is basement and to exploit its technique are used. The use of ionization radiation made it enter on a large scale in our minds. To recover our health, the same ionization radiation are used. It is good practice that the technique to protect ourselves against this ionization radiation we know and talk otherwise all of the technique and technology we turn against ourselves, against humanity. This activity today is a school to perpetuate the very existence of humanity. I would like to encourage you to keep this torch lit to light up our world, particularly in Africa. I will end by saying long life to this collaborative platform. Thank you so much.
Thank you very much, Lansina, for those wonderful closing remarks. And just last, a small request to all the participants and speakers, if we can have a group picture to capture this moment of this webinar, we would like you to open your cameras and have this group picture together of all of us, if it's possible. So please, let's just wait a few minutes while everyone is opening their cameras. I see some people with their cameras on. So at the count of 3, please help me to give me your best smile. So 1, 2, 3. Thank you. Let me just take one last picture, and I think this will help us also to appear in the RPNS-YN bulletin. We've been invited to be part of these articles that they've been producing recently. So one last picture, please stay with me, bear with me for a few seconds, and give me your best smile. 1, 2, 3. Thank you very much. That's all from my side, and I would just like to thank you for staying with us, and our deepest apologies for not following the original agenda. We will try our best for our next edition, and apologies for this. And Margaret, please, over to you for any additional remarks. Thank you.
Thank you very much, Florencia. Mine is just to echo your sentiments, just to appreciate you especially for being a big part in making this a success. To our speakers, Valeria and Mohammed, we appreciate whatever was presented to you actually echoes very well with whatever is going on in Africa, in Kenya, and even in our university. So we really appreciate, and we will appreciate if you could share with us your slides so that we can also share them with the larger community. Otherwise, thank you. And I hope we keep interacting. Thank you very much, Florentia. And to
Thank
the
you.
audience, we appreciate it wouldn't have been successful without you and your participation. We appreciate you. Thank you.
Definitely. So we wish you to have a very good rest of your day, and thank you, Mrs. Valeria, Mr. Mohammed, for being part of this of the webinar content, and we hope to keep collaborating with both of you.
Thank you.
Thank
Bye.
you. Have a very good evening there,
Have a great
everyone. Thank you. You too. Thank you so much.